Hi, I'm going to be talking about my project about the numerical study of ice adhesion. Ice and aircrafts are never a good combination and has always been an issue to the aviation industry. Pilots fear the thought of having to potentially navigate icing in flight. Engineers also have to design the aircraft in such a way to prevent accretion. When it comes to aviation, ice accretion has led to hundreds of fatal incidents dating back to the 19th century all the way to present time. Now, the question that is in all your heads is, how is ice bad for airplanes? Well, first of all, what is icing? Icing in general is any deposit or coating of ice on an object caused by impingement and freezing of liquid. When taking a look at this picture, one will believe that ice only accumulates on the surface of the aircraft, whether it be the wings, propeller, and/or windshield. However, ice can also collect on the sensors, antennas, vents, and cowlings, causing major component failures. In fact, aerospace engineers do not find the weight of an ice significant when compared to the airflow disruption it causes, as it leads to effects on lift, thrust, and drag. To make it more challenging, there are two types of ice, each having vastly different effects on aircrafts: rime and glaze ice. First, rime ice occurs at temperatures below -15 degrees, when the droplet completely freezes at the point of impact with little to no spreading of the ice, while glaze ice occurs between the temperature of 0 to -10 degrees Celsius. But instead of freezing instantly, it will flow and freeze over a larger surface area from the point of impact. In some cases, you get a mix of both, and therefore you get the bad features of both types. As you can see, as a pilot, it is incredibly challenging. You want complete control of the aircraft, but ice hinders that by creating imbalances on that aircraft. This is why for my summer CUSRA project, I was working with Dr. Ali Dolatabadi to create a numerical study on ice adhesion strength in mode 1 fracture, which is in the tensile direction. To go into a little bit of detail, the target of the numerical study is to create a stress field in the crack development plane, which is the interface between the ice and the coating. The crack develops through the application of an external pressure, or in this case, what we used was an air pressure. The stress considered will be the maximum principal stress for tensile tests. The project will look to understand the effect of the type of ice formed on different substrates through mimicking of an icing wind tunnel that was designed by the 2017 Capstone Group. This wind tunnel replicated flight ice conditions and the effect of ice accretion on the aircrafts. The icing conditions were on an aluminum sample and a never wet treatment, which is essentially a super hydrophobic coating with the pressure applied to the ice. The study was carried out through finite element analysis using the software ANSYS. The samples used by the icing tunnel test rig were modeled in ANSYS, and the design models were simplified from the real specimens. In this case, as you can see, the top portion was ice, the bottom portion was aluminum, and the middle was the coating. What's happening here is in this space, there would be the external pressure, which was air coming up and hitting that ice or applying its pressure onto that ice. The reason it's a slice rather than the whole model is that ANSYS will take a long time if it was fully modeled, and it will take a long time to computate that, while the slice will take much less time while giving the same results. Again, the samples used in the icing tunnel test rigs are modeled in ANSYS, and the boundary condition and loads used in ANSYS were adapted from the real boundary condition and loads. All in all, this will lead to data acquisition that will allow the study of ice accretion more efficiently through simply changing the parameters, and eventually a coating that one day would prevent ice to adhere to an aircraft. Thank you.